Well, hello, class. Well, I'm glad that's as interesting as you're making it sound. Now, here's another thing we're going to do with vectors in our cube. It sometimes is useful to find the angle from a vector to each of the coordinate axes. In other words, axes, I should say. That's plural, axes. Sorry about that. In other words, what's the angle between our vector and I, or our angle between the vector and j, or the angle between the vector and k, or if you want the angle between the vector and the x-axis, the angle between the vector and the y-axis, the angle between the vector and the z-axis. I'm sure that's used in navigation and in certain forms of engineering as well as physics. So, if we call these angles from v, for the vector v to I, j, and k, or vector v to x-axis, y-axis, and z-axis, the direction angles of vector v, then alpha, beta, and gamma, respectively, are cosine alpha, cosine beta, cosine gamma, are called the direction cosines of vector v. So what that means is, when we want to find the angle between vector v and I, we just use this formula. Yeah, this one, to find those angles. Now, that might seem like it's going to be a challenge, but it's not a challenge at all, because if you think of vector v as v1, v2, v3, when you dot vector v with I, all you're going to get is v1 plus 0 plus 0, divided by the length of v times the length of I, but that's just 1. So the cosine of alpha, and that's the angle between the vector v and the positive x-axis, or between the vector v and the vector I, if you want to call it that. The direction cosine is just v1 over the length of v. Ooh, I didn't mean to do that. There. Similarly, the angle between the y-axis, or the vector j, and our vector v is going to be 0 plus v2 times 1 plus 0 times v3. That would be the dot product of our vector v with j over the length of v times the length of j, which is also 1. And similarly, the cosine of gamma, the angle between our vector v and the z-axis, is v3 over the length of v. Here's a sketch of the, I hope I made a plausible sketch. We got our xy plane and the z-axis coming out of it, and there's some vector. This is not in the xy plane. As you can see, I got a little angle here showing it from the z-axis going up like this, so I hope you see that. But alpha, beta, and gamma are the direction cosines. Actually, those are direction angles. Cosine alpha, cosine beta, and cosine alpha, cosine beta, and cosine gamma are the direction cosines. So, interesting enough, interesting consequence is that v divided by the length of v, in other words, this is a unit vector in v direction, is going to be v1 over the length of v times I plus v2 over the length of v times j plus v3 over the length of v times k. If you think about that, that's very logical. And since this is a unit vector, then the cosine squared plus cosine squared plus cosine squared equals 1. In other words, this squared plus this squared plus this squared equals 1, because this vector, or this vector, another way to write it, is a unit vector. So the sum of the squares of the cosines of the direction angles equals 1. Okay, let's do an example with this. Given the vector I minus j plus 2k, find the direction cosines. Remember what they are. They're the angle between the vector v and the x, y, and z axis, respectively, or we could call it between the vectors I, j, and k, and show that the sum of their squares equals 1. Okay. So also give the angles between v and each of the coordinate axes. Okay, so we're going to do everything over this one. First of all, cosine of alpha is 1, v1, see, divided by the length of this vector, which is the square root of 6, right? Square root of 1 squared plus negative 1 squared plus 2 squared, square root of 6. So cosine of alpha is 1 over the square root of 6. Cosine of beta is negative 1 over the square root of 6. Cosine of gamma is 2 over the square root of 6. That's simple. And what else was we supposed to do here? I got the direction cosines. Show that the sum of their squares is 1. So, okay, square this, you get 1/6. Square this, you get 1/6. Square this, you get 4/6. 1/6 plus 1/6 plus 4/6 equals 1. Done. Okay. Also give the angles between v and each of the coordinate axes. Okay, well that's not straightforward, but it's not terrible. Alpha, I guess, would just be angle whose cosine is, so oh, I didn't mean to do that. That's right, my software calls it angle whose cosine is. That's what the A stands for. Sorry about that. I think on your calculator it's like cosine to the -1 power, but I have to do what my software tells me I must do, so that works. And by the way, well, I guess if you want to see the others, it's pretty obvious what they are now. Beta would be equal to angle whose cosine is -1 over the square root of 6. I like the way I type this better if I do it like this first. I know it seems weird, but I like the negative to be not in the numerator. So that's the way I have to type it then. And of course gamma is equal to angle whose cosine is 2 divided by the square root of 6. And I'm not going to bother you with finding what the degrees of these angles are, because these are the exact values right here. If I go calculating degrees, I'm going to wind up with some decimal approximation, whereas these answers are exact. By the way, note that the angle between vector v and the positive x-axis is acute, but this one is obtuse. That one is bigger than 90 degrees, and this one is less than 90 degrees. If I were to say, which of these angles is the smallest? You would say, why, the one with the largest positive cosine, thinking that cosine of 0 is 1, right? So the answer is yes, the angle between v and the z-axis is the smallest angle. This is the next smallest, and this is the largest. Matter of fact, this one is greater than 90 in degrees, greater than pi over 2 in radians.